Hello everyone. Today we are going to train a model which will generate handwritten digits. We are going to use MNIST dataset and autoencoder architecture. So before that, if you haven't subscribed, you please subscribe to my channel so that you get this kind of videos whenever I release. And please do like and share with your friends. So let's get into this. So this model will be a autoencoder model. If you don't know about the architecture of the autoencoder, I'll briefly summarize. I'll briefly show you how the architecture works, and then we'll go into the coding part. And also I will show you how you can use the model. I'll also show you how to test the model, and then we'll move forward. Okay, so let's get started. So the autoencoder architecture is like consists of two parts. One is encoder and other one is decoder. So let's say the MNIST dataset is 28 by 28. So this goes into the encoder part. This is the encoder. Okay, and after it passes through the encoder, it will give a output. So this is a, we call it as a latent space. Okay, so this latent space, we consider it mostly lower than the input of the encoder, 30 or something. So this 30 dimensional vector will have the information of this 28 by 28. So it encodes the input of the images, and it produces a space. It's a different space, so it produces a data which can be used in the decoder part. So after this we have the decoder. So this decoder will take the latent space, and then it produces 28 by 28 matrix. So this matrix we will then, so in training, so this is the actual, this is the output, and we can consider this as an image which got reconstructed using this image, right? So I have already prepared a script. This is a Python script which will download the MNIST dataset, and then first I have imported torch and torch vision. So the data is in torch vision, so we will import it from there. These are the hyperparameters that has been given here, and you can skip this for now. So we are now, after that, here if you see, we have two loads, training and testing. These we are loading for the training. And if you see, this MNIST function has the parameter called train, and then if you put it true, then it will download the train set, and then if you put it false, it will download the testing set. So after that, this data loader is there, so it will load the data in batches. So here you can give the batch size. So if you see in the hyperparameters, the batch size is there. If you can tune this hyperparameter as per your GPU memory. If you are using a GPU to train the model, if you are using a high config GPU, you can use this, you can use a high batch size. Otherwise you can keep it 128 or lower. Then this is the model architecture. So it has two parts, as I have already told you, encoder and decoder. So this encoder, I'll go layer by layer what happens in this. So this is a sequential model, and in this one there are multiple linear layers and multiple activation functions in between the layers. First, this is the first layer, 20. So what it does is it takes the input as 28 by 28. So as you know, all these images are of 28 by 28 resolution. So this is the input to the first layer, and this layer will give us the output as 512. So this is the output dimension of the first layer, and then we use this activation function, ReLU activation function, and then similarly after that we are again using a linear layer which again decreases the dimensionality of this 512 to 256, and so on for the next layer as well. And at the end we take that output of the previous linear layer of 128 dimension, and then we produces a dimension of this latent dimension. So usually here we are again using 64 dimension. So this matrix will have like 64 parameters, 64 values, and this is the latent space I was talking about, right? So this encoder will generate this part, and then after this after we get this compressed image from this encoder, we again decompress it using the decoder. So decoder is the reverse of the encoder. It takes the latent dimension, which is 64 in this case, and then it produces 128 dimensional vector similar to this but reverse of this layer, and it uses activation in between as well, and then so on. At the end we get this 28 by 28 output. So this at the end we have this tanh activation function. So this tanh activation function, as you if you know, it produces the output in the values will be between -1 and 1. Okay, so that is it. So this is the forward function. I'll come into this after creating the model and in the training, what happens in the forward function. Okay, here we have created a model using the model class, and we are providing this latent dimension. If you see here in the hyperparameter it is written 64. Then this model is there, this criterion, this is the loss function that we are using, this is mean square root, and we are using Adam optimizer for the parameter optimization. And this is the training function. Here are the number of epochs. If you see in the hyperparameter we are providing 50 number of epoch, and for each epoch this loop is there, and then it takes the batches of the training data. So as we have defined 128 batch size, so this will create a batch of data which will have 128 images of 28 by 28 resolution, and it goes into the model. So this function, what it does is it calls the forward function of the neural network. So here if you see the forward function, it takes the input of this model, this is x, and what it does is it changes the dimension. So it will produces this will be 128 and this will be 28 by 28. So it flattens the images, right? So this x then goes into the encoder. So this encoder has this part. Encoder is like this sequential model, right? So this is 28 by 28 is input, and it gives the output of 64 dimension. So this is the latent that we were talking about, and it gives this latent. This latent will go again into the decoder, and decoder will reconstruct the image from the latent space, and this reconstructed we need to since this is already flattened, right? So we need to expand it to 28 by 28. So here if you see this, again this view function is there, and then reconstruct the size of 0 data, which is 128 again, and this 1 is there, and then after that for each image it produces this 28 by 28 pixels, right? So then we are returning this reconstructed image, and yeah, which is here to this reconstructed image is again used to calculate the loss. So here if you see this criterion, here we are using the reconstructed image and then the data that which we have given to the model. So it calculates the loss between these two values, two vectors, and then we optimize the model, we back propagate the model using this loss, right? Here we are printing the epoch number and batch and the loss of each 100 batch, right? Okay, so this is the function to train the model, and there are some evaluation function also. Before that I'll start the training. And so if you haven't installed on this Torch Vision, Matplotlib, NumPy, you can install all those. You can create an environment variable and install those. Otherwise you can use a Docker, or you can install directly on your system as well. And the script name. Okay, so so this will download the data set first. If you see, this folder is there, data, and then it downloads the data in this raw folder. Then here if you see, it started training. In the first batch the loss was 0.92, and gradually it is decreasing in each batch. So this I have defined the number of epoch as 50. You can if your loss is not reducing, then you can use this tweak this number of epoch. The training is completed now. So these are so as you can see, I have reached loss 0.0171 at the epoch 50. You can train it more if you want, but if you see my training loss in this graph, so it started from this top, and then gradually it decreases, and at close to epoch 50 it is around 0.01, right? So there is no need to train it again, because it, if you see, this graph started giving linear loss. And this part is done. And if you see the other functions, what are the other functions after the training, this is the evaluation script where we calculated the test loss. And in this stats you can see the test loss is 0.01, which is good, which is similar to the training loss, because this is an unseen data set for the model, right? So it has generated same loss for that data. And in the script, if you see, there is one more function, visualize reconstruction. So what this function is doing is, it is taking the data from the test data set, and it is taking eight images for now. You can use different numbers here. It is reconstructing the image, and then we are plotting that image into a figure. So this is the file, reconstruction comparison. So if you open this file, you can see this is the input. This original is the input, which is taken from the test set, and it has reconstructed similar output. Okay, so this as you can see, this autoencoder is mostly generating the images very properly. Whichever we are giving as an input, it is producing this, it is capable of producing similar image in the output. And after that we have one more function which is generate digits. So what this function can do is, so if we remove the encoder part, we have only the decoder, right? And this both are separate modules, so we can use those separately. So in this function, what we are doing is, we are taking some random input of size of the latent dimension, which is 64, and then we are giving that to the decoder. So the decoder is generating some new images from that latent space, right? We can take it as a random digit, new digit generator, where we can give different kind of samples to the decoder, and it can produce, it is capable of producing different kind of outputs, which we don't know what what we can get. So this is like, this is some output from the random latent input, and the decoder is generating some random numbers which we don't think these are readable. And this is what we are doing in this function, and after that this states we are saving that model in this file, so which we can load it in the test, in the testing purpose, or if you want to deploy it somewhere, you can take this checkpoint. And these are the training parameters which I have already shown you. This not the parameters, the states that I have put in the text file. So I'll upload all of this in GitHub, and I'll share all of this with you. You can create your you can change anything in this architecture, in this script. So we have one more script, test script. So this will test the model in different scenarios. You can go through this. I'll not go through this script now. And this script can generate a lot of testing, analyze the models, and visualizations, and you can check everything here. So this is it for this video. If you like it, then please share with all of your nerdy friends, and please subscribe to my channel. Thank you. Bye.